Yes, welcome all to the online classes. I'm Mukesh Bhardwaj. Today, I'm going to start in the continuation of the wave nature of light. In the last class, we had started with the introduction of the wave nature of light, and we had introduced or come to know the topics like reflection, refraction, and refraction indices, and we had seen so many examples related to refraction and reflection and various laws associated to the refraction and reflection. Now, in continuation to that, I'm moving forward and start with the Snell's law. And Snell's law is basically, and before starting to the Snell's law, I would like to give a brief review on the quantum theory of light. The quantum theory of radiation was given by Max Planck in order to explain the black body radiation spectrum. He postulated that the energy of a radiation oscillator is not an arbitrary quantity, must be an integral multiple of h nu, where where nu is the frequency of the radiation and h is a new fundamental constant known as the Planck's constant. Its value is 6.63 into 10 to the power minus 34 joule second. However, the concept of photon, quanta or packet of energy of light was introduced by Einstein in order to explain the photoelectric effect. Photoelectric effect. Einstein proposed that an electromagnetic wave of wavelength lambda equals to c upon nu can be regarded as the collection of massless quanta, each of which has energy h nu. Thus, light wave can be considered as a stream of light quanta called photon. The energy of one photon of light of frequency mu is h equals to h nu, and we know that lambda is given by c by nu. Therefore, we may also write E equals to hc by lambda. The momentum of the photon is p equals to E by c, or p equals to h by lambda. The rest mass of the photon is m naught is equals to root E square by c square minus p square, and it is come out to be 0. So therefore, the rest mass of the photon is 0. Now, we had covered these topics, the index of refraction, and now we just move to the Snell's law. And Snell's law is given as laws of refraction. It is the laws of refraction. N1 sine theta 1 is equals to N2 sine theta 2, whereas theta 1 is the angle of incidence and theta 2 is the angle of refraction. The experimental discovery of this relationship is usually credited to Wilbur Snell and is therefore known as Snell's law of refraction. Uh, he is a Dutch mathematician, 1591 to 1626. He states that the ratio of the sine of angle of incidence to the sine of the angle of refraction is a constant whose value depends on the nature of the two medium. So Snell's law is nothing or Snell's law of refraction is nothing. It is the ratio of the sine of angle of incidence to the sine of angle of refraction, and it is constant. It is constant, but it values depending upon the nature of the two mediums. If medium 1 is vacuum, then V1 equals to C, and the index of refraction of the medium with respect to the vacuum is N equals to C by V. So, by the use of this Snell's law, we can calculate the refractive index of some substances, and the refractive index of air is almost 1. For glass, it is near about 1.52. For glass or fused quartz, it is 1.46, and for diamond, it is 2.42, and for water, the refractive index is 1.33, and if I'm talking about the case of ice, then the refractive index of ice is 1.31, and the refractive index of benzene is 1.50, and same is for the plexiglass. So this is known as the Snell's law, and it is already been covered. We had discussed the quantum nature of light also. Now, moving further, prism, a ray of single wavelength light incident on the prism will emerge at an angle del from its original direction of travel. Del is the del is called the angle of deviation, and phi is called the angle of, or phi is the apex angle. Phi is the apex angle. Now, Huygens principle. Huygens assumed that the light is a form of wave motion rather than a stream of particles. Huygens principle is a geometric construction for determining the position of a new wave at some point based on the uh, knowledge of the wavefront that preceded it. All points on a given wavefront are taken as point source for the production of spherical secondary waves called wavelets, which propagate outward through a medium with speeds characteristics of wave in that medium. After some time has passed, the new position of wavefront is the surface tangent to the wavelets. Huygens construction for a plane wave at a t equals to 0, the wavefront is indicated by the plane A dash. The points are representative sources for the wavelets. After the wavelets have moved to the distance c delta t at a new plane BB dash can be drawn to the tangent to the wavefronts. The pictorial representation or the diagrammatic representation of the wavefronts are shown. The new wavefront is drawn tangent to the circular wavelets radiating from the point source on the original wavefront. So, old wavefront, new wavefronts, old wavefront if I'm talking about the circular, and the new wavefronts. The inner arc represents part of the spherical waves. The points are representative points where wavelets are propagated. The new wavefront is the tangent at each point to the wavelet. The law of reflection can be derived from the Huygens principle. AB is the plane wavefront of the incident light. The wave at A sends out a wavelet centroid centered on A toward D. The wave at B sends out a wavelet centered on B towards C. This wavelet was sent out by wave 1 from a point A. This wavelet was sent out at the same point by wave 2 from point B. So from the mathematical triangle ABC is congruent to triangle ADC, we get some relationship cos gamma is equals to BC by AC. Cos gamma dash is equals to AD by AC. Therefore, cos gamma equals to cos gamma dash and gamma equals to gamma dash. This gives theta 1 equals to theta 1 dash. This is the law of reflection, which we had already done. Uh, Huygens principle, the law, or laws of refraction. If I'm talking about the laws of refraction, so ray 1 strikes the surface at at time interval delta. Later, ray 2 strikes the surface. During this time interval, the wave at A sends out a wavelet centered at A toward this. This is the pictorial or diagrammatical representation of refraction. The wave at B sends out a wavelet centered at B towards C. The two wavelets travel in different media. Therefore, their radii are different. Now, from triangles, we conclude some geometrical relationship BC and ADC. We find that sin theta 1 equals to BC by AC equals to V1 delta upon AC, and sin theta 2 equals to AD by AC, V2 delta upon AC. The preceding equations can be simplified to sin theta 1 upon sin theta 2 equals to V1 by V2, but sin theta 1 upon sin theta 2 is written as N2 by N1. And so N1 sin theta N1 equals to N2 sin theta 2. This is known as the laws of refraction or Snell's law of refraction. Now, dispersion. So before starting to the dispersion, I will like to put some light on reflection of light from plane surfaces. Some facts. The reflection from plane surfaces obeys the following laws, which we know that. Just wait a minute. So before starting to the dispersion, I need to discuss some facts about the reflection of light from a plane surface. The reflection from a plane surface obeys the following laws. The angle of incidence equals to the angle of refraction. The incident ray, the reflected ray, and the normal all lie in the same plane. Images. A real image is one through which the rays of light actually pass and which can be formed on a screen. The virtual image is one through which the rays do not actually pass, although they appear to come from it. The image produced by a plane mirror is virtual. Its distance behind the mirror is same as the object's distance in front of it. The image is literally inverted, that is, it is reversed left to right. The inversion of left right symmetry is called perversion. It's called perversion. Does a plane mirror produce a virtual, perverted, and same size image? Plane mirror. I'm not talking about the concave or convex mirrors. I'm talking about the plane mirror. So the plane mirror produces a virtual, perverted, and same size image. Uh, some facts. The focal length and the radius of curvature of a plane mirror are infinite. This means the power of a plane mirror is 0. The magnification of plane mirror is 1. That is, the size of image equals to the size of the object. The left side of the object appears as the right side of the image. That is the lateral inversion or perversion. If the object moves with the speed u towards a fixed mirror, the image also moves towards the mirror with same speed. The speed of the image relative to the object in this case is 2u. If the mirror moves with the speed u towards away from the fixed object, then the image appears to move towards or away from the observer with the speed 2u. If the mirror moves away or towards an object by distance z, then the image moves away or towards the object by a distance 2d. If a mirror is rotated in the plane of incidence by an angle theta, then the reflected ray is turned through an angle 2 theta. On reflection from a plane mirror, on reflection from a plane mirror, a ray is deviated through an angle del. On reflection, the velocity, wavelength, and the frequency of the light does not change, but the amplitude or intensity of the reflected ray is less than that of the incident ray. Reflection from a smooth plane surface is called regular. In regular reflection, a pencil of parallel rays is reflected as a pencil of parallel rays. Reflection from rough plane surface is called irregular. In irregular reflection, a pencil of parallel rays on reflection get diffused. The twilight is caused by the diffuse reflection of the sunlight from the dust particles, water vapor, etc. The minimum size of the mirror required to see full size image of one is equal to half the height of the observer. The minimum size of the mirror required to be fixed on the wall of a room so that an observer in the middle of the room can see full image of the wall behind him is 1/3 of the height of the wall. Plane mirrors are used in optical lever, sextant, kaleidoscope, periscope, seeing round corners, dental mirrors, telescope. Reflection from a denser medium introduce a phase difference of pi. Now, inclined mirrors, number of images. Suppose two plane mirrors are inclined at an angle theta. Uh, Suppose two plane mirrors are inclined at an angle theta. Let an object is placed in front of the two mirrors. The number of images are formed due to multiple reflection on the two mirrors. The number of images formed is determined as follows. So case first, when 360 degrees exactly divisible by theta degree. That is 360 divided by theta is an even integer. Then number of images formed is 360 divided by theta minus 1. Whatever may be the location of the object. Whatever may be the location of object. Case second, when 360 degree is exactly divisible by theta and 360 divided by theta is an odd integer. The case first is for even integer. If 360 is divided by theta and even integer come out, then number of images can be given by 360 upon theta minus 1. And if 360 divided by theta gives an odd integer, the number of images formed is 360 divided by theta minus 1 for symmetrical placements. For symmetrical placements. In case of even integer, location can be anywhere. Whatever may be the location of the object. Okay. But in case of the odd integer, the number of images is given by 360 by theta minus 1 for symmetrical placement. And if the symmetrical unsymmetrical placement is there, then the number of images is given by 360 upon theta. Case number third, when 360 is not exactly divisible by a theta, then number of images formed is equals to integer value of n, where n is equals to 360 divided by theta. A summary table, I just give it to you in the verbal way. Suppose if theta is 30 degree, so 360 divided by theta come out to be 12. So number of images, symmetrical placement 11, unsymmetrical placement 11, because 12 is even integer. Now if I just take for example, if I take theta equals to 120 degree, theta equals to 120 degree, then 360 divided by theta come out 360 divided by 120 give 3, that is odd. So at the symmetrical placement there will be two images, and if the unsymmetrical placement is there, then there will be three images. So this is some small review about the reflection of light at plane surfaces, or refraction of light from a plane surfaces. Now refraction at plane surfaces. So we need to summarize the some facts. Reflection and refraction. So refraction can take place without change of path also when incidence ray is equal to refracted equals to 0. The deviation of incident ray when it is refracted is by an angle del is given as I minus R mod. On refraction, the frequency of light does not change. This is very important. On refraction, the frequency of light does not change, but both the wavelength and the velocity changes. So the wavelength and the velocity will change. So velocity can be find it out by c by mu, and the wavelength can be in a medium can be find out by wavelength in vacuum upon mu, where mu is the absolute refractive index of the medium. C is the velocity of light in the vacuum, and the V is the velocity of light in the medium. The symbol for refractive index has been changed from n to mu. For air, for some mediums, like for air, refractive index is 1, which we had already discussed. Therefore, when light passes from air into any transparent solid or liquid, the refractive index is always greater than 1. The refractive index of medium 2 with respect to medium 1 is mu 2 equals to first mu 2 equals to mu 2 upon mu 1. A medium 2 is said to be optical denser in comparison to medium 1 if mu 2 is greater than mu 1. Wavelength of color of light, uh, wavelength or color of light and temperature of the medium. Refractive index decreases with increase in temperature. Refractive index does not depend on the angle of incidence. When the medium is same on both the side of a glass slab, then the deviation of the emergent ray is 0. That is, the emergent ray goes parallel to the incident ray. The refractive index of glass with respect to water can be expressed as 9 by 8. So these are the some fundamentals and some facts related to the refraction and the reflection. Now dispersion. Dispersion for a given material, the index of diffraction varies with the wavelength of the light passing through the material. The dependence of an on wavelength is called dispersion. This dependence of n, that is refractive index, index of refraction. So the dependence of refractive index on wavelength is called dispersion. Snell's law indicates light of different wavelengths is bent at different angles when incident on a refracting material. Next, variation of index of refraction with wavelength. The index of refraction for material generally decreases with increasing wavelength. Violet light bends more than red light when passing into refractive material. Refraction in a prism. Since all the colors have different angles of deviation, white light will spread out into a spectrum. Violet deviates the most, red deviates the least, the remaining colors are in between. The colors in the refracted beam are separated because dispersion in the prism causes different wavelengths of light to be refracted through different angles. The rainbow. A ray of light strikes at a ray of light strikes a drop of water in the atmosphere. It undergoes both reflection and refraction. First, refraction at the front of the drop. Violet light will deviate the most, red light will deviate the least. At the back surface of the light is reflected. It is refracted again as it returns to the front surface and moves into the air. The ray leaves the drop at the various angles. The angle between the white light and the most intense violet ray is 40 degrees. The angle between the white light and the most intense red ray is 42 degrees. So the pictorial representation, the violet light refracts through larger angle than the red light as shown. While observing the rainbow, the highest intensity light traveling from higher raindrops towards the eye of the observer is red, whereas the most intense light from the lower drop is violet. If a raindrop high in the sky is observed, the red ray is seen. A drop lower in the sky would direct violet light to the observer. The other colors of the spectrum lie in between the red and the violet. Double rainbow. Some of the time we had seen that there are the two rainbows seen in the sky during the rainy season. The secondary rainbow is fainter than the primary. The colors are reversed. The colors are reversed. The secondary rainbow arises from the light that makes two reflections and from the interior surface before exiting the raindrop. Higher order rainbows are possible, but their intensity is low. Total internal reflection. It is a phenomena called total internal reflection can occur when light is directed from a medium having a given index of refraction toward one having a lower index of refraction. Possible direction of the beam are indicated by the ray numbered 1 through 5. In the pictorial representation, as you see that the possible direction of the beam are indicated from ray 1 to 5. 1, 2, 3, 4, 5. The refracted rays are bent away from the normal since n1 is greater than n2. Critical angle. This is a particular angle of incidence that will result in an angle of refraction of 90 degree. This angle of incidence is called the critical angle, theta c. Sin theta c equals to n2 upon n1. For angles of incidence greater than the critical angle, the beam is entirely reflected at the boundary. This ray obeys the laws of reflection at the boundary. Total internal reflection occurs only when light is directed from the medium of a given index of refraction towards a medium of lower index of refraction. Fiber optics, an application of internal reflection, that is, the basic working principle of fiber optics is on the basis of total internal reflection. Plastic or glass rods are used to pipe light from one place to another. Applications including medical examination of internal organs, telecommunication. This is the construction detail of an optical fiber. The transparent core is surrounded by cladding. The cladding has a lower refractive index than the core. This allows the light in the core to experience total internal reflection. The combination is surrounded by the jacket. A flexible light pipe is called a optical fiber. A bundle of parallel fiber shown can be used to construct an optical transmission line. So this is the wave versus particle nature, Huygens principle and diffraction we had seen. Huygens principle can now explain the law of refraction. We had already covered. These are the some pictorial representation. Why the mirage are seen to us in a sunny hot days? Highway mirages are due to gradually changing index of refraction in heated air. So mirage appears to be seen just to gradually changing index of refraction. So this is the interference Young double slit experiment. We will start this Young double slit experiment uh, just a little bit later. Before to that, I'd like to discuss dispersion overview. What do you mean by the dispersion? Uh, that is, when we had seen that there is a refraction through a prism. The refraction of monochromatic light through a prism is had we had seen in the figure in the previous slides. The two refracting surfaces are shown over there. The angle between these two refracting surfaces is known as the prism angle. Uh, the angle of incidence and the angle of emergence is E, which we had seen in the diagram in the previous slide. And if mu is the refractive index of the material of the prism, then mu is given by sin I upon sin R is equals to sin E upon sin R2. The angle between the incident ray and the emergent ray is known as the angle of deviation, that is delta, which we had also discussed. For reflection or refraction through a prism, it is found that I plus E is equals to A plus delta. R1 plus R2 is equals to A. It's some mathematical concepts which you can go through some reference books, and in that reference book you find some relationship. So dispersion, the separation of white light into its component colors, is called dispersion. Dispersion is nothing. Dispersion, the definition of dispersion is that separation of white light into component colors is called dispersion. The band of colors is known as spectrum. The spectrum of visible light contains Vibgyor. everyone is very much familiar about or aware about WebGear, stands for violet, indigo, blue, green, yellow, orange, and red. Dispersion occurs because the index of refraction is not strictly a constant for a particular material, but rather varies slightly with wavelength. For example, we had already discussed that index of refraction of a crown glass for red light is 1.51, whereas for violet light it is about 1.53. In case of a prism, the dispersion is most pronounced because the two refracting surfaces are inclined. For small angle prism, a mathematical formula, that is delta red is equals to mu red minus 1 into A, delta violet is equals to mu violet minus 1 into A. Uh, so some facts about the spectrum, because the band of colors is known as the spectrum, which is obtained by the dispersion, that is the white separation of white light into the components color is known as dispersion, and the band of colors is known as the spectrum. So some fact about the spectrums are: a spectrum in which the constant constituent colors have sharp boundaries and are distinctly visible is known as pure spectrum. Impure spectrum: in this type of spectrum, various colors mix. To obtain the pure spectrum, one uses the following arrangements: band spectra, absorption spectra, Fraunhofer lines, and fluorescence. It is a process by which body absorbs short wavelengths of light and subsequently emit longer wavelengths. So this is all about the dispersion. Now in the next lecture, we will start with interference, refraction, and diffraction. And before ending to this lecture, I would like to discuss some questions. When a pebble is dropped into a pond of still water, what happens? What happens? The pebble moves. When a pebble is dropped into a pond of still water, what happens? A particle moves, wave moves, the pebble moves, water moves. A wave moves. The perfect answer is a wave moves. Mechanical waves are called elastic waves. So mechanical waves are not called elastic waves. The statement is false. What are the essential properties a medium must possess for the propagation of mechanical waves? So, what are the essential properties, or which of the essential properties a medium must possess for the propagation of mechanical wave? Stable pressure, maximum friction, constant temperature, minimum friction. Maximum friction or minimum friction? What are the essential properties of a medium must possess for the propagation of mechanical wave? Obviously, minimum friction is needed to be provided for smooth propagating of the mechanical waves. Now, sound travels through a gas under which of the following condition? Isothermal condition, non-isothermal condition, adiabatic condition, transverse condition. So sound travels through a gas under which of the following condition? Through a adiabatic condition. What kind of wave is formed in organ pipes? Mechanical waves. A wave transmit momentum cannot or can't it transfer angular momentum? No. What is the most fundamental property of wave? temperature, pressure, frequency, wavelength. Almost all are the properties of wave, but the fundamental property is the frequency. Fundamental property is the frequency. Which among the following is not a suitable phenomena to establish that light is a wave motion? Light is a wave motion. Interference, diffraction, reflection, polarization. So, reflection is not a suitable phenomena to establish that light is a wave motion. Interference is the suitable phenomena to establish that light is a wave motion. Diffraction is same and the polarization. Now, this numerical, the optical path of monochromatic light is same if we travel 2 centimeter thickness of glass or 2.25 centimeter thickness of water. If the refractive index of water is 1.33, what is the refractive index of the glass? So the parameters are with you. Put in the formula and get out the refractive index using the Snell's law. Identify the condition for which it is not necessary for two light waves to be coherent. The two waves must be continuous. The two waves should be of the same frequency of the wavelength. They should have a constant or zero phase difference. The two light source should be narrow. So this two light source should be narrow is not necessary for two light waves to be coherent. So this is all about the wave nature of light, refraction, reflection, dispersion. Okay, a light wave enter from air into glass. How will the energy of the wave be affected? The energy of the wave decreases. A light wave enter from air into glass. How will the frequency of the wave be affected? It remains unchanged. Which among the following is an example of coherent source? Fluorescent tube, LED light, lasers, tungsten filament lamps. So laser is the example of coherent sources. So these are the some questionnaires related to the wave nature of light. Now in the next class, we are going to start with interference, Young's double slit experiment, and further some more topics in continuation to the interference. Thank you. Thank you to all. Thank you.